This is part 2 of using signature analysis on old radios. In part 1, I went over a little bit about the technique and told you that I would develop a chart for this Zenith radio that I'm working on, but I wanted to show you something today. This, of course, is the SIG 101, and if you have not watched any of the previous videos, especially I would recommend you watch part 1 of this so far 2-part series on using signature analysis on old radios, but especially if you don't understand signature analyzers, you might want to go back and look at some of the other videos that I've done on both general signature analyzers, including the one built with the analog discovery, and especially the ones on the SIG 101. What you see here is an ellipse indicating a capacitor. Before I show you the circuit, notice the frequency that I'm using over here, 100 kilohertz. And that is of importance because what I am actually looking at is the plate of the output, the audio output tube, the 6K6. Now, you probably will say, well, so what's interesting about that? Well, the fact is the plate of that tube is completely isolated. And I'll show you that in a second on the schematic. But this ellipse indicates a capacitor, and by the way, you may notice that I'm using the capacitor device. These others might be useful for various purposes, but for this particular series on using this in an old radio, I'm going to stay with capacitor unless I tell you otherwise. And by the way, also on the far right, you can turn on enable measurements, and it'll tell you what the resistance and capacitance is. And right now, it's telling us that there's this 4 nanofarads of capacitance. Now, I don't know why it says 3K ohm, because that should be close to infinity, but I don't really pay a lot of attention to these measurements, although in a little bit I will show you that sometimes this particular capacitance measurement can be remarkably close. Okay, now let me show you the circuit. I've gone back to the enlarged schematic for the receiver, for at least the audio and power supply sections, because in part 1 I talked about the fact that I had unplugged the speaker from the back, which in essence disconnects this field coil, because there's a 4-pin plug. These are 2 of the pins. Well, the other 2 are these 2. That is this end of the transformer and this end, which means that pin 3 of the 6K6 is essentially isolated from ground. In fact, it's isolated from the circuit except for the inter-electrode capacity inside this tube. Now, what I am going to do is pull the 6K6 and see what happens to the trace on the screen. Okay, I have pulled the 6K6 entirely out of the circuit. So earlier I was speculating that this may be due to the inter-electrode capacitance inside the 6K6. It obviously isn't. It must be due to capacity between leads in the chassis. Now, let me show you what happens as I reduce the frequency. I'm going to go back down to, say, 10 kilohertz. And you see you get a much smaller ellipse. Earlier we were using 60 cycles to test out the power supply. That would be about here. And there you see it looks like an open circuit. I did this to show you something, that eventually we're going to change the frequency away from 60 hertz, particularly when we start doing these analyses inside the RF sections, because 100 kilohertz is a more reliable, or maybe closer to the truth frequency for working in the RF circuits. But I thought it might be interesting for you to see that even in the audio circuits, if you drive the frequency high enough, you start sensing capacitance, in many cases just stray capacitance in the leads and things of that sort. So, okay, let's move now to the next little segment. I want to go back in time and talk to you about Ryder's resistance measurement system for radios, and then we'll take a look at the chart that I told you in part 1 that I would prepare. Here is the title page of a book published by John Ryder in 1932 entitled Servicing Receivers by Means of Resistance Measurement. Now this particular copy is a printout of a CD I bought many years ago, published by a group called Radio Era Archives, in which they collected a bunch of old manuals on radios and put them on CDs. This is from the Radiophile Volume 2 of that set. If you want to try to look for that, it's Radio Era Archives and Tubes and More. That is, the Antique Electronics Supply in Arizona used to sell these CDs. I don't know if they still do. But you see, it prints out into a pretty good-sized manual. Now, of course, I'm printing it single-sided here, and I'm sure the original book was printed front to back, so it would be half this thick. But nonetheless, it's a fairly substantial book. Let me give you an idea of the scope of the book by showing you the table of contents. Now, you'll notice, a little bigger here, that it starts out simply talking about some things that I'm sure all of you already know about resistance and the types of resistors and what happens when you connect them in series and parallel, and here resistance in power packs. Of course, they were talking there about the battery eliminators, is what we would call them today. And finally, in chapter 4, it gets to resistance in tube circuits. As you see, it talks about everything from RF transformers to tapped coils. Then in chapter 5, it talks about point-to-point resistance measurements, and then checking condensers, which of course today we call these capacitors. Applications of the ohm meter, working through the sockets, and of course, as you know, we've been doing that using the Zenith radio. Servicing receivers by means of resistance measurement. Now, in this, he throws in the situations where you might want to use other methods, like he talks about measuring line voltage. But basically, I'll show you this next section, and then we'll move back to the actual testing. He talks about various tests and dead receivers and so on. Then analyzing special circuits using Ohm's law and so on, condenser tester specs. This is for a tester that he has developed. It's actually very similar to one that Mr. Carlson uses, and actually these have been around for quite some time. I have a couple of old ones. They use an RF signal, a few hundred kilohertz, to measure capacitors, and the nice thing about that is that it measures the capacitors in circuit. They can be kind of useful, but they're also a little bit tricky to use. So at any rate, this is measuring by the resistance method, or testing by means of resistance. If you want to go get this book, I think you can actually still buy paper copies of it from old-time bookstores. Sometimes copies show up on Better World Books, which is the outlet for Goodwill Industries and so on. Anyway, let me now show you the chart that I prepared and the measurements that I got using the ohm meter, the capacitance range of the ohm meter, and then the signature analyzer, the Sig101 relative to ground, and then those same measurements relative to what I called common, which is, you might also call the B- bus. So, as I told you in the last part, I used a code here where EF means E flat, in other words, an ellipse flat, like the one we just saw a few minutes ago. E angled, where it's at some angle close to 45, and then E up, where it is more or less up and down. Now, understand, up and down means very low resistance in parallel with a capacitor. Angled mean the capacitor and the resistor have approximately the same reactance at the frequency you're using. And then EF means that it is predominantly the capacitor and a fairly large parallel resistance. So, here are the ohm meter readings that I got. None of them really surprised me very much. What did surprise me a little bit is when I measured these capacitors, for example, it showed 9 microfarads on pin 8 of the 6X5, which of course that's the input capacitor for that pi filter, so I expected to get 9 microfarads. What is also interesting is the screen grid, which is connected to this same point, also reads approximately the same thing. And what it got was a something between EF and EA. In other words, it was higher than 45 degrees on the angle, but not quite up or flat. I'm sorry, I just told you wrong. It was lower than 45 degrees. In other words, it's between EF and EA. So it's between flat and up 45 degrees. So let's say 22 degrees or 25 degrees or something like that. The rest of them, except for pin 8, which, remember I told you that pin 8 and the screen grid are essentially connected together, came out like this. Now, what's interesting is the plate of the 6K6 came out flat, but you can understand that because that is the transformer. Remember, that's this thing, and it's disconnected. So pin 3 is basically just connected to the tube and the inter-electrode capacitances of the circuit, but otherwise it doesn't have any other connection. And you see it reads like 5 nanofarads of capacity, so very small stray capacitance there. When I went over and did the measurements using the common, I got quite different results in some cases. For example, I got infinity on the cathode of the 6Q7, whereas I got only 158 ohms, but we'll look at the schematic here and you'll see why that is true. If you look at the schematic, you see that the cathode is connected through this 150 ohm resistor, which actually measures 158 ohms. So you would expect that. And when you measure relative to the common, which is here, rather than to the chassis, there is no DC path from the cathode to B-. The DC path is to ground. So these are the numbers I got. What I also discovered is that the Sig101's ability to measure capacitance is actually quite good. When I, for example, put the Sig101 on here instead of the multimeter and measured it, it got around 8.9 or so microfarads. So I have found this to be useful, but one of the things that I think might bear a little analysis is to now compare these readings to the schematic and see if we can understand where we might be able to find some defective components and where this doesn't add anything to the basic resistance and capacitance measurements. Before we actually look at those numbers, though, I do want to cover something that I said I would in part one that I would do, which is to show you how this was actually measured. Now, the test probes I used are some very pointed, I don't know if you can see how sharp that one is, very pointed test probes. And I do that so that you can easily break through any dust or grime that's gathered on the contacts over the years. Since I'm using these tube socket adapters to do everything, all of this from the top of the chassis, this really isn't necessary, but when you're working on old equipment especially, or even new equipment that's been in an environment where there may be some plating on the outside of the contacts, it's a good idea to use a very sharp test probe. The other side of the signature analyzer has been connected either to the chassis for those measurements or to the common for the second set of measurements. The capacity and the resistance and capacitance measurements that I show were done with this X-Tech meter. It has, of course, a resistance scale and has a capacitance scale. One reason I like this meter is it does auto range in every scale. So when you test a resistor, whether it's 10 ohms or 10 mega ohms, it will auto scale to show you that. Similarly, the capacitors auto scale so that a 5 nanofarad capacitor will show up with the same number of digits of precision as a 5 microfarad capacitor, for example. So those are the way that I tested for the columns that I've shown. By the way, I thought I might, since I've been talking about an old book by John Ryder, plug a book that you used to also be able to get from Antique Electronic Supply. I don't know if you still can. Fixing Up Nice Old Radios by Ed Romney. Now, this is not a part of the Radio Era archives. Apparently, Antique Electronic Supply, which also goes by Tubes and More, apparently printed these out and bound them. And one nice thing about them doing that is they printed it double-sided, so this would be twice as thick if I had printed it out myself. At any rate, this Fixing Up Nice Old Radios by Romney is probably, in my opinion, if you're going to have just one radio book on restoring old radios, I get this one. Now, there are some great books by Ghiardi, G-H-I-R-D-I, I don't remember. Anyway, some really good books, and maybe in some future video I'll talk about some of those that are a little more theory, and they're very nice, but this is really how to fix old radios from the standpoint of a modern technician trying to repair old radios. And by that, as you see from the cover, it's radios that go back to just around World War II and all the way back to World War I. So very nice book. Hope it's still available, but I'm not sure if it is. Wasted enough time? Let's take a look at the actual values we got. And as we do so, I'll insert the schematic so you can see what we're talking about. We'll start with pin 3 of the 6K6. That's the plate. I remind you that's this, but the transformer is disconnected. A little later I'm going to reconnect the transformer and the field coil and repeat some of these, and if any of them are different, I'll show you those at the end of this video. So it shows in infinite resistance at pin 8, which you would expect since this is disconnected. It shows 5 nanofarads of capacity using the meter, and the SIG 101, by the way, I think showed 4.9. In other words, very close to 5 as well. Of course, it showed a flat, an EF trace, that is a flat line. I'm sorry, E means ellipse. This isn't an ellipse. It's just a straight line. Infinite ohms to common as well. Of course, it doesn't matter if this is disconnected. Doesn't matter what you measure with respect to. And the same 5 microfarads to common. So let's see if we can figure out how that could have happened. I think I just wrote that down wrong. I think that's nanofarads. Actually, now that I look at it, I'm just reading it wrong. It is an N, nanofarads. All right, now let's look at the screen grid, pin 4. And for that, we'll have to go back to this schematic. You notice pin 4, which is the bottom of the transformer also, comes down to B minus. Remember, B minus is taken to ground through this 0.05 microfarad capacitor. And B minus is also the negative side of these filter capacitors in the power supply. So what did we get there? Well, we got 2 meg with respect to chassis, but only 4 ohms with respect to common. And of course that's what we would expect because it's connected to common, but common is not connected to chassis. So basically 2.2 meg is the resistance reading between the common line and the chassis. 9 microfarads for capacity, and once again, that is this capacitor here, C17, which is connected directly to pin 4. I got an EFEA ellipse, that is halfway between a flat ellipse and an angled ellipse. And I mentioned 4 ohms and 160 picofarads of capacity to common. Grid 5, which is the control grid, this pin here, had 750K to chassis, which you will notice that there's a 470K resistor, and then if you follow me down, and then a 100K and a 50 ohm and a 150 ohm. So we'll disregard those and basically say there's 100K here and 470K there. So this may read high. I may want to go in and check that resistor and make sure that it's actually a 470K, because I have tested, I said capacitor, I meant that resistor. I have tested this resistor, and it is roughly 100K. I think it's about 112K, but still close to 10%. By the way, old resistors, particularly carbon resistors, tend to go up in value. So if you measure across them and you find a value that's high, it's almost certainly a bad resistor, that is if it's out of tolerance, because even if there are shunt resistances in the circuit, they would reduce the resistance. So if it's above the value, it's got to be out of tolerance. That's one of the things, and maybe at some point in a future video I'll talk about some of the little things that I was taught that help when troubleshooting these old radios, things like that. The fact that if you measure a resistor in an old radio and it reads out of tolerance high, you know it's bad, because you don't have to worry that, well, maybe there's another resistor somewhere shunting it, because if that other resistor is shunting it, it should read low, not high. Okay, 760 picofarads for the to ground or to chassis, a flat or basically open circuit to chassis, infinite ohms to the common, 760 nanofarads, so remarkably consistent, and once again a flat with regard to common. Finally, the cathode, pin 8, 245 ohms to ground, and that is these two resistors in series. Remember, this is pin 8 to ground. 114 picofarads to ground, or to chassis, I should say. A slightly angled, I guess on this one I wrote EFEA, and this one that's actually I'm sorry, no, this is an ellipse. This is an angled straight line, indicating some resistance, fairly high resistance relative to the frequency that we're operating, 245 ohms. Infinite resistance to common, 10 microfarad reading on capacity to common, and an EF or E flat ellipse to common. And what's interesting is this is a straight line, whereas this is a slight ellipse. Well, my meter is telling me that I've been talking too long, so let me run through the rest of this fairly quickly, and then we'll close this video. So on the 6Q7, pin 3, which I remind you is the plate, it's connected through a 220K resistor to common, and it shows infinite to chassis, which we would expect, 760 picofarads, complete open on the signature analyzer, 260K to common, however, and it says it's 220. So this resistor may be a little out of tolerance because it shouldn't be more than about 240K, and it's showing 260. 820 picofarads for capacity. Then the top cap, and by this I mean the top cap lead, not the top of the tube, because I have it disconnected from the tube. 1.1 meg. The top cap, remember, is the grid of the 6Q7 right there. 1.1 meg, 114 picofarads, flat line, open. This is all consistent. Infinite to common, 60 picofarads, and a flat line. And finally the cathode, 158 ohms, which is this resistor, just barely, well, no, it's within tolerance, because 10% would be 15 ohms. So it could be up to 165 and still be within tolerance. It reads 158 ohms, 108 picofarads, a nice sloping ellipse, sloping line, indicating the 158 ohms of resistance. Now notice, by the way, that this resistor is tilted up a little higher than this one, which was 245 ohms. So remember, the flatter it is, the closer it is to infinity. The more it swings up, the more that the lower the resistance, so that a short is straight up and down. With respect to common, I got infinity, 10 microfarads, which I would expect, 10 microfarads, and an E-flat ellipse. In other words, an ellipse that looks like this. And then I took one more set of measurements on the 6X5, just with respect to pin 8, which is the cathode. And of course, with respect to common, it'll be shorted, so I didn't do them over here. I didn't do anything with respect to common, but I did do them with respect to chassis. 2 meg to chassis, 9 microfarad, which you would expect, because through this capacitor and 100 ohms or so, you should get you should read about the 9 microfarads. This is supposed to be an 8, but it actually reads 9 microfarads. And an EFEA reading. And what that indicates is that this capacitor is in series with a resistor to chassis. And of course we can see that that's exactly what happens. This capacitor is in series with these resistors to chassis. So that explains the EFEA. Okay, what I have determined here, or at least in my mind, what I take away from all of this is that the signature analyzer adds a little bit to the analysis, but in all candor, it doesn't add a lot, because if you consider the effect of the resistor and the capacitor, which you can measure with a modern multimeter, the signature analyzer does not add a lot. It just simply tells you that, for example, when you have a resistor and almost no capacitance, you're going to get an angled line which is proportional to that resistance. When you have a fairly large capacitor, you're going to get an ellipse that has some angle to it. The ellipse will be proportional to the capacitor, and the angle will be proportional to the resistor. So, my conclusion is that signature analysis on old radios, at least in the power and audio sections, isn't terribly useful. It doesn't give you a lot of new information that you couldn't have gotten with the same method and a multimeter. I'm going to do some additional experiments, and if they prove to be of any interest, I'll do a video. But if you don't see a part 3, it's because I did some of these same tests in the RF and IF sections of this receiver, and in my opinion, did not find the signature analyzer to be particularly useful in that application. So I hope that you learned something from this. I certainly did. I hope you enjoyed it, even if you didn't learn anything, because some of you out there probably know 10 times as much about radios as I do. But at any rate, whatever you got out of it, I hope you'll look forward to some more videos, maybe or maybe not, on signature analyzers and old radios. But at any rate, while you're waiting, please have a nice day.